Um, Hi, this is Bob Westervelt. It's a pleasure today to introduce Klaus Ensslin from the ETH Zurich. I've known Klaus really for quite a long time. I used to go visit Art Gossard, who grew molecular beam epitaxy samples for us all out at Santa Barbara. It was always great to visit in the wintertime. And I met Klaus there, who was enjoying the benefit of the same facilities and working on sort of similar things. He got his PhD from the Max Planck Institute in Stuttgart, then did a postdoc in Santa Barbara, and is now at ETH Zurich. He's quite a well-known person in the nano community, nano semiconductor community, and has a variety of honors. One, he honorably took on the job of running the ICPS International Conference at Zurich, which is a terrific amount of work, and they don't pick you to do that unless they're quite happy. He's also a fellow of the APS and has a number of other awards. Today, he's going to tell us about energy gaps and quantum devices and twisted graphene layers. Klaus.
Thank you, Bob. It's a great pleasure to be a guest of your seminar series. I highly appreciate the invitation. And of course, it would be nice to be all there and see you guys, but at least we can meet over Zoom. So we'll talk about energy gaps in quantum devices, in twisted graphene layers, and also in non-twisted layers. I will start out with non-twisted layers and then move on to the twisted layers. On the bottom, you see my collaborators, and I will mention them as I go along. So let me start with the famous band structures of silicon and gallium arsenide. I think many of you know them well. This is from the book of Z from 1981. You see the nice indirect gap in silicon, 1 electron volt, 1.5 for gallium arsenide. And we all know that these gaps are relevant for transistors, and they're also relevant if you want to build a qubit. Now, when you think of graphene, it is, of course, a perfect 2D material. We all know it has no gap. It has this linear dispersion. So at first glance, you would argue, if you want to build something like a qubit, it has advantages because naturally abundant carbon is 99% nuclear spin free. So hyperfine coupling should be weak. Carbon is one of the lightest elements we have. It's element number 6 in the periodic table. So spin orbit interaction is supposed to be weak, so expect long spin coherence times. And of course, that's not specific to graphene. That should be true basically for all carbon-based materials, unless there is some funny twist of the geometry. But there is no gap, so no dot, no qubit. What can you do? So what we do is we take bilayer graphene. Bilayer graphene still has no gap, but rather than having a linear dispersion, it has a parabolic dispersion, at least very close to the charge neutrality point. And if you break the symmetry of bilayer graphene by applying a vertical electric field, you open a band gap and you get this Mexican hat dispersion. And if you blow this up, it looks a little bit like that. And here are typical numbers. You can get band gaps of the order of 50 millielectron volts if you have electric fields of the order of 1 volt per nanometer. And also that idea is quite old, and you see the theory and experiment results from way more than 10 years ago. If you blow this up again, then you come to what is sometimes called a Mexican hat, and which is a few millielectron volts in height, of course, also depending on the gate voltages that you apply. All of this is very well known. Now, let me quickly tell you how we build our samples schematically. So we start out with a piece of graphite, a large piece of graphite, which is very flat. Then we deposit a layer of hexagonal boron nitride from our Japanese colleagues, a stripe of bilayer graphene, another layer of hexagonal boron nitride. Then we etch down to the graphene flake and make ohmic contacts. We also contact the back gate. Then we add another layer of insulator and the top gate on top of the entire stack. This is how a typical sample looks like. And I'll show this to you in a more schematic way. You have a source and a drain contact. They are connected to the bilayer graphene layer below the surface. You have this top gate here and the back gate. And in this region, particularly here, you can apply a vertical electric field. You have 2 degrees of freedom. You have a top gate and a back gate. So you cannot only change the band gap, but you can also adjust the position of the Fermi level in that band gap. So let me show you a typical result. And it actually took us almost 10 years to get to that result. It looks rather trivial, but there is a lot of technology and physics behind that. What you see is the resistance that we measure between source and drain in a situation where we have a large vertical electric field between top and back gate. And in addition, we have the Fermi energy in the band gap. And you see that we do observe some activated behavior. If we take an Arrhenius kind of analysis, we find a band gap of like 55 millielectron volts. And we find resistance values at low temperatures up to 10 to the 10 ohms. And these 10 to the 10 ohms are probably limited by our cabling. The resistance of the device could be even higher. And the early devices in many labs around the world, they all suffered from the fact that there was a nice band gap, but the resistance values were never very high. So this is different here. We can have very high resistance values. That's much higher than h over e squared. And that makes it possible to build quantum devices. So let me start out with the simplest quantum device there is, which has a long history in gallium arsenide, which is a quantum point contact. So you see this device on the right. The only difference to the device on the left is that now we have a split gate geometry, and we apply a voltage between one of those split gates and the back gate. And as before, we gap the system and we position the Fermi energy in the gap. And then we send a current between source and drain, and the electrons have to flow, or holes have to flow through this little gap here in the center. Now, if this were gallium arsenide, we would just take these split gates, we would apply a more negative voltage and laterally squeeze the channel. In graphene, that's not possible, because as I make these voltages more negative, what I would do is I would change the gap below these gates, and in addition, I would drive the Fermi energy out of the gap. So I'm not allowed to touch these split gates. So what remains is to deposit another insulator and another gate, and a gate that just controls the chemical potential in this little region in the quantum point contact itself. And what you see now on the left is the conductance of this device as a function of this little channel gate here in the center, while all the other gates are fixed, and they're fixed to the situation that I mentioned before, maximize the gap and position the Fermi level in the gap. So what you see is a very nicely quantized conductance, well known from gallium arsenide, long sought for in graphene. In many devices, there are very early experiments in Amio's group where he built a very similar device in suspended bilayer graphene. And what you can see very nicely here is that the quantization occurs in units of 4 e squared over h, and the 4 comes from the fact that you have a degeneracy of 2 for the spin, like in most semiconductors, and another degeneracy which comes from the valley degree of freedom in graphene. There are lots of interesting things in these quantum point contacts that makes them much more interesting than in gallium arsenide, but I don't want to go into the details here. In particular, you have this Mexican headlight band structure, which leads to topological effects, which you can actually probe in this very simple quantum device. Of course, you can break spin and valley degeneracy by applying a magnetic field. And what you find is that the G factor for the electrons, the spin G factor, is 2. And we can have a valley G factor that is tunable because it depends on the band structure. And that can be tuned in a range of 20 to 120. So it's 1 to 2 orders of magnitude larger than the Zeeman splitting. Now, let's go one step further. Let's build a quantum dot out of that. So on the right-hand side, you see the schematic. There are source and drain contacts. Then the blue regions are the regions which are only gated by the back gate. Then you see 2 extended split gates on the top and the bottom, and they're gated in a way that you get a depleted area below them. That's the white area, that's non-conductive. And then you see this little red gate on the top. And again, this tunes the chemical potential right there on top of the device. So if we look on the left-hand side, we see the schematic band structure. Source and drain contacts are macroscopic. The Fermi level is positioned in the valence band. In this little constriction, the Fermi level is also positioned in the valence band, and we measure some conductance of the device. So if we now make this gate voltage more positive, what happens is that we move the Fermi level in the gap in this little constriction, and the device is completely pinched off. And as we keep going, what happens is that we start populating the conduction band locally, and we start seeing nice Coulomb blockade oscillations. So let me number them. This is electron number 1, 2, 3, and 4. And people who know gallium arsenide know that it took a long time until we started believing and that you can go to the few electron regime. But in graphene, this is actually quite straightforward. Can also be done by charge detection, but also by other arguments. The nice thing is that all of this is completely gate defined. So what you can do is you can reverse your gate voltages. You make your outside region not p-doped, but n-doped. And then you start accumulating in the center holes rather than electrons. So in the very same device, you can have a quantum dot filled with electrons or holes. And in particular, you can build something like a double quantum dot, where one quantum dot, for example, contains a hole, while the other one contains an electron. Let me just show you one specific feature of this quantum dot, which I think is quite nice and easy to understand. I show you now the filling of the first 24 electrons into such a quantum dot. And you see that the peaks are almost equidistantly spaced. This is what we expect because the dominant energy scale is Coulomb energy, Coulomb charging, and that's the geometry of the device. So you see on overall, the spacing decreases as you fill in electrons, which is because the dot gets larger. But what you see in particular is that once you have filled in the 4th electron, there's a larger gap. Once you have filled in the 12th electron, there's a larger gap. And once you have filled in the 24th electron, there's another larger gap. On the bottom panel, you see the distance between the peaks, and you see there's a maximum for 4, for 12, and for 24. Now, what happens? If you fill in the first electron in the system, it goes into the 1s state. Now, the 1s state is fourfold degenerate for the reasons I mentioned before, 2 for spin, 2 for valley. That means the first 4 electrons, they go into the same orbital state with 2 spins and 2 valley quantum numbers to be filled. Then you have to go to the next orbital state, which might be the p state. The p state in 2 dimensions for a proper geometry can be degenerate. So you get a factor of 2 for orbital degeneracy, 2 for valley, 2 for spin, that gives 8. And these are electrons 4 to 12. But now something interesting happens as you go from 12 to 24. So you need something that has something of a degeneracy of 3, and that cannot come from the arguments that I just mentioned before. So on the left-hand side, you see a simulation of the equipotentials in this dot, and they are rather circular. And that is the reason why actually the p orbitals are degenerate. On the right-hand side, you see a single particle calculation done by Angelika Knote from Manchester. And she calculated single particles without interactions, without spin, without valley. So you see just the different energetic states. So look at the top right figure. You see the lowest state here is not degenerate. The next 2 are degenerate. That would be the degeneracy of the p states. And then you move up there as you fill in electrons. Now, the same calculation has been done for a larger quantum dot. The top one is 80 nanometers. The bottom one is 200. And suddenly you see that all of the states develop a 3-fold degeneracy. And this 3-fold degeneracy comes directly from the band structure of bilayer graphene. In bilayer graphene, for low energies, the equi-energy lines are circles. That's only true for low energies. If you go to higher energies, you see the trigonal warping of the band structure. And as we apply very large vertical electric fields, this trigonal warping starts playing a role even for the low energy states. And that means for large quantum dots and the corresponding spatial symmetry, you start to see these 3-fold degeneracy. So what that means is that the electrons, number 12 to 24, they start filling the dot potential gets screened, it gets larger. You start having this 3-fold degeneracy that comes from trigonal warping, and then you have 3-fold orbital degeneracy, 2 for spin, 2 for valley, and that's the other 12 electrons here. So we understand quite well how this works. And now let's measure how we fill these states. What you see here is the position of these Coulomb resonances as a function of an in-plane magnetic field. In plane means that we only couple to the spin degree of freedom, not to the Valley degree of freedom or other orbital degrees of freedom. And you see very nicely that the first two Coulomb peaks move to the left to lower energy, and the next two move to the right to higher energy. The red dashed line indicates what you would expect for an electronic G factor of 2. And you see nicely that the first two electrons come in with the same spin, but all opposite Valley degree of freedom. And the next two come with the opposite spin, but parallel, and again with opposite Valley degree of freedom. If you go to the next 8 electrons, which is what we call the P shell, you again see that the first 4 come in with the same spin, the next 4 come in with the opposite spin. And you can plot all of that. The slopes you can convert to a G factor, and you see we go from -2, +2, and then come 4 electrons with -2, 4 with +2. And then for the next 12, life gets more complicated. It's not exactly 2 anymore. Also, experimental noise starts to become bigger. And one needs to invoke interaction effects to understand this in more detail. But overall, we have a very good understanding how we start filling carriers into these graphene quantum dots and how we can use them for more complex experiments. And let me just flash you a few other results. You can now turn the magnetic field and have it perpendicular to your sample. That means you also couple to the Valley degrees of freedom. And the Valley degrees of freedom are much more pronounced. I told you the Valley G factor is 1 to 2 orders of magnitude larger. So here for a small quantum dot, we can fit the splitting between the two lowest states in magnetic field. We find a Valley G factor of the order of 30. And if we go to a larger quantum dot, we make it larger in real space, which means we squeeze it in K space. And that leads to a Valley G factor, which is 70 or so. So we can actually tune the size of the Valley splitting by the size of the quantum dot, which is a pure electrostatic tuning. So if you think of something like a Valley qubit, this is actually a very nice property because of a huge tuning range over the two-level splitting that is relevant for the qubit. Okay, now also just flashing this here, Pauli blockade in double dots. This is an essential feature that you need in order to measure spin coherence times. This is a very complicated experiment because you have spin and Valley degrees of freedom. I just show you here the result at relatively high magnetic fields where you see nice spin blockade, very similar as in gallium arsenide. And if you go to lower magnetic fields, then actually this interplay of spin and Valley becomes interesting. And we also started doing time-resolved experiments using a charge detector, of course, inspired by what has been going on in silicon and gallium arsenide and other systems. And you can nicely see by pulsing the system that you can see how an excited state is unloaded and the ground state is loaded again. You see the schematic on the left. We start out with a ground and excited state below the Fermi level. Then we raise the system such if the electron were in the ground state, it would just stay there. If it were in the excited state, it would leave and the ground state would be refilled. And then we go to the unload situation where both states are above the Fermi level. And the fact that sometimes we just see the single feature here allows us to measure population of the excited state. And on the right-hand side, you see a plot of the count rate as a function of time. It behaves exponentially as it should. And the next step is now to understand this in more detail and learn more about coherence properties in these novel quantum dots. So let me summarize this first part of my talk. I think graphene quantum dots are really nice. They offer a lot of opportunities that go way beyond what we know in semiconductors. They're also more complicated, and complicated usually means interesting. Okay, now let me go to the twisting part. And this is, of course, like bringing coats to Newcastle. Many of you guys are very involved with that and have been leading that field. You see the moire pattern as it arises when you twist these two layers. And of course, the interesting part is that also in K space, we start rotating these two hexagons versus each other as we twist the two layers with respect to each other. I want to start out with a few experiments which are at unusual twist angles. By unusual, I mean they are not at the magic angle. So let's do the first experiment. I show you here a schematic which is actually from the first paper by Kuo from MIT, from Pablo's group. So you see how if you have these two cones basically in K-space, then the distance between these two cones, or the points, where the charge density is 0, the distance depends on the twist angle. And as you tune this twist angle, you can start coupling these bands, and you can arrange flat bands that lead to all this fantastic physics of mod insulators, superconductivity, and so forth. But you could also think of a large twist angle. And if you have a large twist angle, that means basically that you have two graphene layers, and the carriers, if they want to move from one graphene layer to the other, that means they have to move from one cone to the other, they need a large delta K. And this delta K, because depends on the angle, can be much larger than the Fermi wave vector that is available in these systems. So what happens is the following. This is, again, the schematic. These are the two hexagons in K space. This is the delta K that you need to go from bottom to top layer. And I should mention here that very similar work has been done in the quantum Hall regime, again, in Pablo's group. So we do a different experiment. We measure Fabry-Perot resonances. So on the top, you see a schematic of that. So think this is now one layer of graphene or two layers of graphene. And you have in between a region which is different from the outside. So you could tune the overall density with a back gate, and this local stripe is tuned with a top gate. Now what happens is if carriers come from the left, they can be reflected at this interface. They can be reflected in that cavity, and that they can leave. Now, usually in 2 dimensions, it's very difficult to impossible to see Fabry-Perot oscillations, because the incidence angle controls basically the characteristic wavelength where you see interferences. And so in general, all of this averages out. However, in graphene, as it has been shown for single layer graphene, and this was pioneered by Philip Kim's group, it does survive. And the reason is Klein tunneling that makes sure that only the electrons propagating under a right angle to the interface can make it to the other side. Now, on the right-hand side, I show you an experiment on perfect bilayer graphene. So same experiment, bilayer graphene, backgate, one stripe of top gate. And you see here, these are the N and N regions and the PPP regions where you don't see Fabry-Perot resonance. But then here on this side, PNP and NPN, you do see very pronounced resonances. And the reason for that is that you don't have Klein tunneling in bilayer graphene. You have actually anti-Klein tunneling, but if you have a large enough displacement field, you have a suppression of anti-Klein tunneling in the band structure because of band inversion, and that works very similarly as the Klein tunneling in single layer graphene. All of that has been published a long time ago, and you see these nice Fabry-Perot resonances. Now what I do is I take, rather than taking a perfect bilayer graphene, I do the same experiment, but with two layers twisted by a large angle. And you see the experimental data on the left-hand side. So right-hand side is perfect bilayer graphene, which we would say is maximally coupled. And left-hand side is a twist angle of order 10 degrees, very large twist angle, but same experimental setup. Now what you see is that there are pronounced resonances, but also other features here. So if you have a look into that lower right region, we can see that if we are in this region over there, this looks roughly like an N and N region on the top layer and N and N region on the bottom layer. And so there is no Fabry-Perot in either of them. However, if we go into this little region down there, we see that we have an NPN structure in one of the layers and none in the other. So we have Fabry-Perot in one of the two layers, but not in the other one. And that gives rise to a nice set of stripes, and you can analyze these stripes and their separation, convert them to a Fermi wavelength, and that works perfectly fine. And then you can go to the rightmost region. There you have an NPN system in the top and the bottom layer. Of course, you change the densities in both of these layers, and that means you have basically two completely independent Fabry-Perot oscillations. And you see that nicely from this cross-hatched pattern. This is the consequence of basically independent Fabry-Perot oscillations in the two layers. So there's no scattering of electrons from one layer to the other that would disturb that pattern. It just looks perfectly fine. So that's the first indication that these two layers basically don't talk to each other, at least electronically. Now, let's have a look at this lower right part here where you see the splitting of the line. This is what we would call the zero density line. So further up here, it's the zero density line unsplit. And then as you increase the displacement field, this line splits. And that basically means that the zero density situation in one layer and the other layer occurs for different gate voltages. And that means that it's quite obvious if you have, for example, a top gate above your boron nitride layer, it affects the top graphene layer differently than the bottom graphene layer. For bilayer graphene, you don't see that in the density because they are so strongly coupled that you have one density for the two layers. Here you have really two separate densities. And this splitting here comes about because the top layer screens the electric field from the top gate, while the bottom layer screens the electric field from the bottom gate. And how much this screens depends on the distance between the two layers. So we can model this with a plate capacitor and analyze the distance between the plates. So on the right-hand side, you see the model. These are two graphene layers. Each of these graphene layers has some electronic wave functions in the z direction perpendicular to these two layers. And we just model this now as if the thickness of each graphene layer were dictated by the wave function. And the distance between these two wave functions is vacuum, which we assign with an epsilon of 1. And that gives us the separation between the two graphene layers. And this is the wave function for different stackings of graphene layers, as well as for the twisted graphene layers. And we find that the separation between the graphene layers is 0.34 nanometers, which is actually exactly what you expect. And in other words, we can also measure the thickness of the graphene layers to be what it is expected to be. So it's interesting that this is an entirely graphene experiment, and we can measure atomic distances from a capacitance measurement. And of course, you could argue that this is the capacitor which has the largest capacitance per surface area, because you cannot bring two conducting planes closer to each other than it's done here in this twisted bilayer graphene system. Okay, so let's now again move one step forward. Now what I'm twisting are double bilayers. So I told you about bilayers before. Now we take two bilayers and twist them with respect to each other. And on the right-hand side, you see what we call this voltage stability diagram, top gate, back gate, and the various lines. So if you go in the main diagonal, you increase the density. If you go in the off diagonal, you increase the displacement field. And then these layers, of course, couple to each other. And again, we go to the regime where the twist angle is relatively large, so that the two double layers are mostly decoupled. So here you see two layers, and we twist them, and something interesting happens. So top gate, back gate, conductance map. And let's have a look what happens at 0, 0. So no gate voltage is applied. The conductance is very low. So what we have produced is an insulator at no applied gate voltage. So how is that possible? Well, let's have a closer look at our sample. Our sample now consists of 4 graphene layers. The top 2 are strongly coupled and the bottom 2 are strongly coupled. The whole stack is embedded in boron nitride. So if you look at the top graphene layer, on the top side, it has boron nitride. On the bottom side, it has graphene. The same is true for the bottom layer. However, the two inner layers, the two inner graphene layers, they have a graphene neighbor on either side. So the boundary conditions for the inner graphene layers and for the outer graphene layers are different. And usually when people do DFT calculations, they assume vacuum on either side. In this case, it's boron nitride. And it turns out that this change of interface leads to a polarity in the graphene layers. And it leads just by construction to a built-in electric field. So you get an electric field in the top layer, which is opposite and equal in size in the bottom layer. Now, that means, we know that already, that applying an electric field to bilayer graphene leads to the opening of a band gap. So the interesting piece of information is here, you take two twisted pieces of bilayer graphene and you twist them with a large angle so that there is no coupling between the inner two layers. And that leads to an insulator on its own. And the built-in electric field is actually quite significant. It's 120 millivolts per nanometer. And you could now speculate that if you replace boron nitride, for example, by some interesting TMD material, you could increase that. And you could build an insulator at will by just twisting layers. So I think this makes the system very interesting. And if you think about quantum devices, that could go in the right direction, that you build an insulator without even applying an electric field. Now, let's change the twist angle a little bit. So you saw the diagram on the left. On the right-hand side, I show you magnetotransport. And you can see how the two Landau fans move through each other, which are the two Landau fans of the two layers that are tuned by top and backgate voltage. So here's sort of a schematic of what you expect. This is the twist angle on the top. So somewhere in this regime, around 1 degree, we have flat bands. The smaller we make the angle, the stronger the layers are coupled. On the other hand, the larger we make the twist angle, the more independently we can tune the layers, the density in the layers, the electric fields in the layers, and so forth. So there's an interesting regime at around 2 degrees or so, where the layers are still electronically coupled, wave functions overlap. On the other hand, you can still assign carrier densities to a specific layer, at least for certain gate voltage ranges. And what I've shown you on the left is a 10-degree sample. On the right is a 1.17-degree sample. You see the insulating state in the center has disappeared. We get new insulating states for fulfilling, and the sample is now in a more strongly coupled regime. So now we go somewhere in between, somewhere between 1 and 10 degrees, which in our case is around 2 degrees or so. And again, I show you a conductance map or differential conductance map as a function of top and backgate voltage. And this is measured at a small magnetic field, 1.5 Tesla, to see Shubnikov-de-Haas oscillations. So there are a lot of wiggles here, and all of these wiggles correspond to Shubnikov-de-Haas oscillations. So remember, this is a bilayer system, 2 bilayers on top of each other, twisted by an angle of about 2 degrees. So what you can immediately see that there are regions out here, for example, or down there, where you have one periodicity. That means we have one band that contributes to transport. On the other hand, there are regions, for example, here or on the upper right, where you see 2 periodicities. So you see there are again 2 bands that contribute. And if you keep going in this direction, there's again a single periodicity. And there are more phases down there where we have again single periodicities or no periodicities at all. So how can we understand that? Well, let's have a look at the schematic band diagram on the top right. So I told you, you can think of the band dispersion. I think you can hardly see me. Let me switch on my light here. Maybe that is a little better. So you see, basically, that's the parabolic band of one bilayer graphene. It's not parabolic, it has a Mexican head, but let's forget that for the moment. And then a certain delta K away in K space, you get the parabolic band of the other bilayer. And the same is true for the valence band. So if there is no vertical field applied, so no displacement field, that means we go along this line over here, you see very nicely what happens. For example, as we fill in electrons, we have 2 bands, 1 band in each of the 2 bilayers. That gives rise to 2 kinds of Shubnikov-de-Haas oscillation. That's that cross-hatched pattern. But as we go higher in energy, higher than this maximum in the band in between, then we are back to a single layer and we get 1 set of Shubnikov-de-Haas oscillations. That is also called a Lifshitz transition. It's a topological transition in K space. And we can measure the energy scales where this happens. We can compare to calculations and so forth. So there's a lot going on there. Now, let's go along a line of finite displacement field. So that's a schematic here in the middle now. So now what happens is we have these two sets of parabolas, and now we start shifting them relative to each other because we apply a displacement field. And now what happens is the following. Let's assume the Fermi energy were here. Then you get one set of oscillations. That's here. Now we raise the Fermi level. The second band becomes populated, and we enter this region of the crosshatch pattern, which is here or here. It's, of course, theoretically electron-hole symmetric. In the experiment, it's never perfectly electron-hole symmetric. So now we start occupying one band, and then the next band as we go through the conduction or the valence band. Now let's go to an even larger displacement field. And now something interesting can happen. We have a situation where at zero total density, we populate the conduction band of one layer and the valence band of the other layer. So now we have something like a coupled electron hole system. They don't talk to each other by scattering because the delta K is too large. But of course, they do talk to each other by Coulomb interaction. So there's a long history of bilayer systems in gallium arsenide. This is an electron hole bilayer system that is coupled by Coulomb interaction. And again, it's probably as close as it can get. It's separated by atomic distances. And that's happening for large displacement fields at very low total density or zero density. So zero density line is this line over here, the off diagonal. So it's happening down here where you see all the oscillations are gone. And same thing on the other side, that you have just reversed the role the two layers play for the electrons and the holes. And it happens also on the other side. So let's have a closer look here. Let's do a measurement right there where this happens. You again see the splitting here, which arises from the screening of the top gate by the top bilayer graphene, same for the bottom gate and bottom layer graphene. And so you have to take this capacitor model into account to understand when is my density zero. So you see the two zero density lines here. That's when the density in one layer is zero. That's when the density in the other layer is zero. And in the middle is the line where the total density is zero. Okay, so here is your schematic. What's happening? We have the two layers. We have the Fermi level in between. We have a huge displacement field between the two layers. And one layer is charged negatively and the other layer is charged positively. So naively speaking, you would expect, well, that should be a good conductor. We have one layer containing electrons and the other one containing holes. If you do the measurement, however, it's not that true. You see here, here's the magnetic field dependence. Here is the density, total density of the system. Here's zero density. And you see at zero density, something remarkable is happening. At higher densities, you start seeing Shubnikov-de-Haas oscillations of each of the two layers. Exactly at zero density and at zero magnetic field, you start seeing a resistance maximum. It's not gigaohms, but it's still quite high compared to the other resistance values in that system. And we can achieve something like 30 kiloohms or so. So rather than lowering the resistance, you increase the resistance by this electron hole state. Now you can measure the temperature dependence of that resistance maximum. You can fit some Arrhenius law and you get a gap of the order of 0.4 millielectron volts, which is a tiny fraction, of course, of the band gap in these systems, but it's yet a remarkable energy if you measure at millikelvin temperatures. And now you go to Alan MacDonald, who was the pioneer in all of these calculations for 2D systems in gallium arsenide and so forth. And Alan, of course, said immediately, this is what you see is a charge density wave or an excitonic insulator. So these two Coulomb coupled systems, they talk to each other. And rather than giving rise to high conduction, they start opening a gap, a completely interaction-driven gap. And this gap gives rise to the high resistance that we observe. And that agrees the numbers actually are quite compatible between the experiment and the theory. And I think this is a nice example how twisting these layers leads yet to another correlated states in addition to the ones that have been observed by others. Okay, now let's finally come to magic angle twisted bilayer graphene. That's, of course, pioneering work by Pablo's group. And I just flash here major figures from his paper. I showed that before. This is how you couple these systems in K-space. What happens if you go to the magic angle? You get flat bands. And on the right-hand side, you see this dispersion of these bands as a function of the various K vectors. Now, here is the data. I'm sure all of you know that, but let me show it anyway. This is the resistance of the device, and you see the superconducting dome. And here you see basically the IV characteristics for various temperatures. Now, we try to do something different. We'd like to build a quantum device with that. And the easiest quantum device with a superconductor to be built is a Josephson junction. And on the left-hand side, I show you the schematic, which I've taken from this paper here. So you take a superconductor and another superconductor and an insulator in between. And the question is now, can the Cooper pairs move easily from one superconductor to the other? Or how thick do you have to make the insulator that this doesn't work anymore? So on the right-hand side, I show you our data, which looks very much like data from other Josephson junctions. So you see the IV trace. Again, you see a supercurrent here for very small current biases. And then you see this hysteretic behavior between up and down sweep of the current, which is characteristic for the capacitive environment of the Josephson junction. It's a well-known phenomenon from other Josephson junctions that have been built, and it shows that this is possible here. So how do we build that Josephson junction? Well, we start out with a layer of magic angle twisted bilayer graphene. We encapsulated it boron nitride, very much the same way as it is done in your groups, graphite backgate. Then we deposit gold gates on top. We deposit another layer of insulator and yet another gate here. So what we have basically three regions now. We have a region between the center gate and the back gate. We have a region between the outer gates and the back gate. And we have a region which is only gated by the back gate. And I should mention there is a very similar paper by Pablo's group, which was published back to back with ours. So we have three densities now, which we call the densities in the leads and the density in the junction. And all of these densities can be adjusted independently with these gate voltages. That's a top view of the sample, and you see all the various gate layers and how we apply our biases. So let's first have a look at the resistance of the device, or on the bottom, the critical current map. You see that in the whole regime, we find a nice region of superconductivity, and we find a tinier region in the electron regime. So what we do is we basically tune our leads, if you want, to this region in the whole regime where we have nice superconductivity, and then we can tune the barrier in between with this gate voltage. So this is what I showed you before. This is basically where we tuned the junction carrier density to a value which is far to the left, and we tuned the leads to the carrier density exactly where we have this superconducting dome, and that's where we see this nice IV trace, which shows that this is a Josephson junction. Now, this device has lots of degrees of freedom that are usually not available for Josephson junctions. So for example, you see here the lead density fixed at this particular value where the superconducting dome has its maximum, and we tune the junction density in a wide range. So of course, if the two densities are the same, then we get a large supercurrent because the entire device is superconducting. But even as we tune the junction density far away from the superconducting point, we see that the supercurrent persists over large regions. So the lead junction interface, in our case, it's determined by electrostatics. It's very different from other Josephson junctions where these are two materials that are close to each other. So there's a Fermi velocity mismatch. The Fermi velocity itself depends, the junction area depends on the Fermi velocity, and therefore we can now build a device where we can actually change the length of the junction. So we can only make the center part insulating or non-superconducting. We could take two of these gates or all three of them. And that's what you see on the right-hand side. So the center junction, the center gate is 100 nanometers in width, and that's the curve that I have shown you before. Again, the lead carrier density is tuned to the superconducting regime, and the central gate is tuned over this regime, and we see a wide range of superconducting behavior. Now let's go to the other extreme where all the three gates are tuned together. Then the total length is 1.4 microns. And you see, we still observe a supercurrent quite far away from where the region in the center should still be superconducting. So this somehow means that the coherence length should be longer than 1.4 microns. We still don't completely understand that. And we are doing more experiments, but it's an experiment that is, I think, hard to do in any other system because you can so easily change the length of these junctions. You can also build a junction that has different superconductors in series. You can do a hole-like and an electron-like superconductor in series. And again, that's something very nice. Now here you can also apply a high frequency signal, which has been used by many scientists before to see Shapiro steps. So here you see the same IV diagram that I have shown before you. The black one is without high frequency applied. The violet one is with high frequency applied, and you see very nice steps here in the current, and that matches to the situation where the frequency matches the characteristic energy of the system. And you can change the power of your high frequency source and measure the critical current, and then you can see these higher order Shapiro steps nicely appearing in the system. So this is almost like a textbook Shapiro experiment. We can also play with the frequency, of course. We can play with the samples, and there are lots of parameters that can be tuned to understand this in more detail. So I think this is a wonderful situation that you have a tunable superconducting quantum device in one and the very same material, everything tuned by gate voltages. Okay, so let me dream a little bit towards the end. So we have Josephson junctions in twisted bilayer graphene at the magic angle. I showed you a lot of quantum dots. All of these quantum dots were realized in untwisted graphene layers, but you could, of course, also think about what would happen if you do that in twisted layers. How could you possibly make insulating regions in twisted layers? And there are many ways. I showed you a couple of them. You could make a correlated state. The correlated states are probably not good enough in the sense that they create a really high resistance. But you could create something like I showed you with the bilayer systems with a large twist angle in between. That could possibly work. You have topology in your system. I mean, people talk a lot about topology in the condensed metaphysics. I think in bilayer graphene, topology is right at your fingertips. You can see the effects of the topology of the band structure in a quantum point contact. We can actually see it in quantum dots. And it leads to characteristic features which you can nail down. It's right there. And then there's the valley degree of freedom. The valley degree of freedom in silicon is also there, but it's usually a nuisance because it's hard to control. In graphene, the valley degree of freedom is very rich. I'm not sure that we have the potential for a good valley qubit, but we can control the valley degeneracies and we can control the valley splittings by a magnetic field and by gate voltages. So it's an interesting degree of freedom that you can tune. If you don't like it, you can tune it away, and you might even like it, and then it becomes useful. So I think this opens the door to build hybrid quantum systems. So if you take all the buzzwords in our field, superconducting devices, you could think about Majoranas, Josephson junctions, quantum dots, all in the same systems, all controlled by gate voltages. And I think that makes this whole zoo of systems, twist angles, and quantum devices a very nice avenue to work on. So let me close here. I thank you for your attention, and I thank my team here. I mentioned the names along the way. I talked about graphene quantum devices. I showed you something about shell filling and valley G-factor tuning, but there are other things. There's interesting jetting along K directions. There's spin control. Also, Kondo effect is interesting because of the valley degree of freedom. And my second part was on twisted graphene layers, mostly large twist angles, where we see layer control, charge density waves. There's an interesting zoo of Lifshitz transitions that you can investigate, and Josephson junctions at the end. So thank you very much for your attention.
Great. Well, thank you so much. A lot of really interesting, beautiful results. Time for questions. We have one in the chat from Tai-Hee Kim. Said, could the monotonic superconducting behavior of the Josephson junction occur due to some impurities, ? What could be the possible origins of the non-monotonic behavior?
So I assume you mean the non-monotonic behavior of the critical current with gate voltage. Is that probably what you mean?
Yes, he says.
Okay. Yes, that could play a role. Of course, as we all know, meanwhile, there's twist angle disorder. And what I haven't shown you because it doesn't look so nice is Fraunhofer interferometry, which will also work on these samples. And it actually looks very nice in Pablo's samples. It doesn't look that nice in our samples, which is probably an indication that there are inhomogeneities in the sample. And I think that that plays a role for these non-monotonic curves, as you call them, yes.
Okay, another question from Yuval Ronan. Do you think the 1.4 micron width of the supercurrent in the Josephson junction might be due to the coherence length of the normal graphene heterostructure rather than the superconducting coherence length ?
Yes, that's a very good question. And I cannot answer that with a yes or no. As an experimentalist, I'm just surprised that we get a supercurrent across such a long junction. So it must mean that some Cooper pair makes it across there. And which one is relevant or whether that's a combination of both length scales, I cannot answer. Sorry. Good question.
Okay, good. I should say to other people, if you would like to ask a question, it's sort of efficient to type it into the chat window at the center bottom of Zoom if you haven't used Zoom much, and then I'll read it. I have a question while they're typing. Could you say a bit about how your very patient graduate students manage to stack so many layers with such precision? Do you use robots or what's the rig that you use to make these?
Well, you know, we're in Switzerland. Our watch industry is still up and healthy. No, I mean, you're absolutely right. And I guess everybody who stacks a twisted layer knows how hard it is. And it's probably no surprise to you that the samples with the large twist angles were not intended, but they were all to be matching angle and turned out to be at a completely different angle that fortunately showed some interesting physics. So I should say, yes, I have to make a big compliment here to my grad students and postdocs who accomplished all of that. The yield for these samples is not as we want it to be.
Okay, congratulations on that. Any last questions? Okay, if not, Klaus, thank you so much again. It is a shame that we're not in the same place. Like you say, we could go to have dinner and it would be good. But we are lucky to be able to hook up across the Atlantic. Yes?
Can I just answer one question from Philip that he put into the talk?
Oh, yes, of course.
Philip, that's a very good question. So I have claimed that two layers with a large twist angle are electronically decoupled. And the obvious experiment is the one you suggest, namely measuring the tunnel current between them. The problem is if you take two layers and you twist them and put them on top of each other, then the edges overlap. And the edges are atomically rough, and therefore they lead to KK prime scattering. So therefore, the two layers are coupled exactly at the edges. So what you need to do is you need to do a tunneling experiment by eliminating the edges. And we have tried that. So you basically need to build something like a Corbino geometry for tunneling experiments, where you deplete the edges and have only the system overlap in the center. We have not succeeded so far, but yeah, we are trying to.
Wow. Okay, any last questions? I'm looking here. Okay, if not, thanks very much, and hope to hear from you soon.
Yes, hope to see all of you soon. Bye-bye.